Hello everyone, so today in this video we're going to talk about rotameters. It's the part 2 of our playlist, and so in the question we're asked to find an expression relating the height of a ball in a rotameter to the volumetric flow rate. So rotameter is a type of device which measures the flow rate depending on how high the ball is located. For example, it's usually done with the gauzes, so the higher the ball means the higher your flow rate is. Now we're doing the rotameter example with the liquid. So the liquid is going to be coming from the bottom, and the ball is going to go until some height. Okay. Yeah, so there's flow here, flow there, flow below the water, below the ball, and like on the sides of the ball and on the top of the ball. And okay, so we're gonna mark 3 positions. So we're gonna mark this position to be position 1, we're gonna mark this position to be position 2, and this is gonna be our position 3. So in order to approach our problem, we can use our force balance equation. So we know that in order for the ball to have no acceleration, so the flow is gonna give some so the flow is going to provide some force, right? So in order for ball not to move, it should be in a force balance. So it should be in equilibrium. So we can use the force balance idea to come up with the solution for our expression of a height and a volumetric flow rate. So we know that the forces that are acting on a ball is the ball has a weight. And the ball also has a buoyancy, right? And okay, let's start before starting. Let's consider some of the variables we have. So we have the diameter of a tube, which we're going to call as D. And so our diameter of a ball is going to be our D0. And what else we have is we have the cross-sectional area here, so cross-sectional area 2, and we're going to have cross-sectional area 1, which is going to be equal to the cross-sectional area at 3, right? So we know that the cross-section tube is we're considering tube to be just straight, right, for now. Okay, so we know that one of the forces we're having is the weight. So that's going to be the mass times the gravitational acceleration, right? So how we can set up our mass is, so it's the difference between the density of a ball and the density of a liquid, and multiplied by the volume, which is mass, and we're going to multiply it by the gravitational acceleration to get the force. So that's going to be the and that's going to be the density of a ball minus density of a fluid, right? Times the volume. So the volume of a ball is, so it is pi times diameter to the cube, diameter of a ball over 6, right? So it is pi r to the cube over 2, but we're like over 3, but we're considering it with the diameter. So that's going to be pi diameter to the cubed over 6. So as we said, this should be equal to the force, as we're considering it to be in a force balance. So the other force that is acting on a ball is the pressure force. So the pressure force is the pressure times the cross-sectional area. So how we can do that is, so that's going to be pressure. So we're going to consider only the what is that? Yeah, only the first section and the third section. So we're going to considering these these 2 points. So like pressure in 1 minus pressure in 3 times the cross-sectional area. So which is going to be the pi d squared over 4, right? Okay, so that's our force balance. And what we can do from here is, so it's clearly pi's are going to cancel, and it is also d0, so these are going to cancel, right? So what we have here is rho, like density of a ball minus density of a fluid times d over 4. So I can say that it as like 3 times 2. I can make that as 3, 2 here. And oh, I just noticed here I forgot g. So this was our mass, right? So but the force is, so this is our mass without including g. And the force is mass times the gravitational acceleration. So I should multiply that by g. And here, in denominator, like numerator, we're going to have 2gd equals pressure in 1 minus pressure in 3, right? Okay. And if we're going to look at our diagram, we can see that the cross-sectional area at a point 2 is very small, right? And when it goes to the cross-sectional area at 3, the flow is staying, we're considering it to be a sudden expansion problem. So when the flow is going from a point 2 to point 3, it is experiencing a sudden expansion, which means there is no pressure recovery. Okay. Then what we're going to do is, so now we have our expression that relates our pressure 1 and the pressure 3. Okay, now we can use the Bernoulli equation and try to apply that Bernoulli equation to see what we can do with that. Okay, the Bernoulli equation is going to be, so I'm going to consider the Bernoulli equation from the point 2 and point 3. And as I said before, as it's sudden expansion problem, the pressure in point 2 is going to be equal to the pressure in point 3. So if I consider the if I'm considering the Bernoulli equation for only point 1 and point 2, I can use the pressure for point 3 to be equal to the point 2. Okay, so I'm going to say the pressure in point 2 minus pressure in point 1 over the density plus velocity at point 2 squared minus velocity at point 1 squared over 2. And I'm going to consider this small change in height to be almost negligible because the height of the diameter of a ball is so small, so we can neglect the potential energy change in our equation. And so there is a frictional heating, but to make our computational easier, for now we're going to consider our frictional heating to be equal to 0. Otherwise, it's going to make our calculations so complicated that it would take us a lot of time. So we're just assuming our frictional heating to be negligible, right? And as I said before, if we want to compare we know that in a rotameter, the flow rates should be equal to each other, right? So flow rate at 1 should be equal to the flow rate at 2, which means the velocity at point 1 times the cross-sectional area at point 1 should be equal to the velocity at point 2 times the cross-sectional area at point 2, right? Okay, and if I want to solve for V1 and replace that V1 from our equation, so our first velocity at point 1 is going to be equal to velocity at point 2 times area at point 2 over area at point 1, right? So I'm going to take that and replace with our velocity at point 1 in our Bernoulli equation. So what I'm going to have is, so I'm going to have this 1. So I'm just factorizing it in one step. That's going to be a1 or no, it's a2 over a1 to the squared, right? And I'm going to make that equal to 0. Okay, that's 0.2. Okay, what we can do next is, okay. Okay, I'm going to go back to my diagram again. So as I said, that let's take a look at the point 2. So the cross-sectional area here, I can assume that cross-sectional area to be almost equal to 0. So I can say that it's so small so that we do not have to consider that. So which means the whole term here can go to 0. So because I'm saying that the cross-sectional here is so small and the cross-sectional of a tube is comparatively big, so that if I divide a very small number by a very big number, it's going to be very near to the 0. So I'm going to assume that to be equal to 0. And the equation I have now is plus v squared 2 is equal to 0, right? And now if I want to solve for velocity at point 2, that's going to be 2 times, so it's going to be negative, so I can change the order of pressure, so it's P1 minus P2 now, and over rho. And if I want to get rid of square, I'm going to take a square root of here. Yeah, so that's now what our second velocity at a point 2 is. Okay, if I take a close look here, now I have like P1 minus, I know what P1, like pressure at point 1 minus pressure at point 3 is equal to. And I also know, because of the fact that being a sudden expansion, I can make that equal to pressure at point 1 minus pressure at point 2, right? So I can get this equation, the left hand side of our equation, and plug it back to the equation I have here, to the velocity, okay? So what I'm going to have now is velocity point 2 is going to be equal to 2 times so 2 times rho, so 2 times rho of B minus the density of a fluid times 2gd, it's the diameter of a ball. I forgot that diameter of a ball here, over 3 rho, right? So I can get this 2 multiplied by this 2, so I can get this as 4 here, and everything raised to the power of 1 over 2, because it's the square root of it, right? So now we have our expression of a velocity at point 2, where in a question, if we read our question one more time, we need to derive an expression relating the height of a ball in a rotameter to the volumetric flow rate. So height. So now we should consider the height, right? But we don't have any height in our equation. So this specific example, if we assume our tube to be straight, we can only find the point such velocity, like there's going to be only one velocity, so that it's going to be in a force balance. So it's not how actually rotameter works, because we need to actually measure the velocity using the height of a ball, but there's going to be one specific height and one specific velocity, so that it's going to be in a force balance. But that's what we want, but that's not what we actually want, right? So now what I'm going to say is, the tube is not straight. So it is kind of structured like this, and we still have our ball. And it is D0, right? But this time, the diameter of a rotameter of a tube is not D. So we should somehow relate that in terms of height, right? So if we assume, we know that this is going to be our height, right? This is going to be our height. So, and this is going to be our D0. So how we can determine our expression of diameter in terms of height is, we can say that our diameter is going to be equal to our D0 plus MH. Yeah. So M here is kind of how steep it is. How it's just similar thing to the slope, right? And I know that the flow rate at a point 2 at that cross-sectional area is going to be velocity at point 1, velocity at point 2 times the cross-sectional area at point 2. So now our cross-sectional area here is going to be the difference between our the cross-sectional of a tube over the like minus the cross-sectional area of a ball. So that's going to be pi d squared over 4 minus pi d0 squared over 4, right? So now what I'm going to do is I'm going to get this equation and plug it in instead of d here. So my Q2 is going to be equal to the V2, velocity at point 2 times, okay, times pi over, so I want to get pi over 4 outside of the equation, and that's going to be d0 squared plus 2mhd0 plus m squared h squared minus d0 squared. Because I plug in the d equation, so diameter equation, back to my equation, and I'm gonna have to take a square of it. So I can see some simplifications happening here. So these d0, so like the diameters of a ball squares are gonna cancel out each other, and now the equation I have is Q2 times like flow rate at point 2 is gonna be equal to velocity at point 2 pi over 4 times 2mhd0 plus m2 height to the square, right? So what I can do now is I already have found my equation for the velocity at a point 2, right? So I'm just gonna get this and plug in to my new equation. So my flow rate at point 2 is going to be equal to it's going to be equal to this thing times this thing. So velocity at point 2 times, okay, let me change that 1 over 2 times pi over 4. So it's going to be times 2mhd0 plus m2h0, right? Yeah. So this is how we can kind of relate our height to our flow rate. So that's what we were asking in our question. So we need to find the expression relating the height of a ball in a rotameter to the volumetric flow rate. So now we have our expression in terms of height and other variables that we already know to find the volumetric flow rate at a point 2. Okay, thanks for your attention.